Hello, this is Systems of Equations video part 4, and in this video we're going to continue on talking about systems that are consistent and inconsistent, and also those equations that are dependent and independent. Now we looked at an example that was consistent and independent. Now we're going to look at when a system is um, independent or dependent, should I say, dependent, and also with infinitely many solutions, and also a system that is inconsistent but has no solutions, but yet there is still some independence with the equation. So we'll look at a couple examples, and let's look at this example where we have 2x minus 3 is equal to y. And then we say that y minus 2x is equal to 1. Now look at the particulars here. So I'm going to help you to recognize what's going on with this. And basically, one equation is in standard form, and then the other equation is in slope-intercept form. Okay. So one way you can look at this and actually see numerically is if you would change both of these, or at least one of these equations to slope-intercept form. So this one is in slope-intercept form already. This one here, this equation y. No, this is in standard form. Sorry, this is in standard form. This is in slope-intercept form. This one is in standard form. So this is in standard form. Standard form. And this is in slope intercept form. So I want to use this. I want to take this equation here to be in uh, convert this to slope intercept form. So what we do is we isolate the variable y by taking negative. Uh, let's just do it. Taking the negative 2x, the term negative 2x, and saying positive 2x to both sides. Taking positive 2x to both sides. So next we have y will equal to 2x plus 1. So now look at this very closely. We have now both of these because I'm going to shift this equation. It's still going to be the same, but I'm just going to switch it where it's still the same look where you have y is equal to 2x minus 3. We have 2x minus 3 is equal to y, but it's the same as y is equal to 2x minus 3. And the reason why I wanted to basically write this, because I wanted to be consistent with the other consistently written as the other equation is 2x plus 1. So it's easier for you to see what's going on here. What's going on is it's easier for you to see that you have, and I'm going to change my colors here, that you remember that I said, and I made a comment in the last couple of videos, that when the slopes are the same, the equations are going to be parallel. What does that tell you? When the equations, or should I say its graphs, the lines are parallel to one another, you know those numbers or the graphs or will never intersect. The lines will never intersect in those graphs. So it will never render a solution. It will never, the lines will never intersect with each other, which will allow a solution to be created. So here in this case, if we were to actually graph this, I'm going to just sketch the graph. And you always read the graphs from left to right. And your algebra teacher should always, that's one of the main things they should have told you that when you start going into graphing and things. So just sketching the graph, we know that the slopes are positive. So we have our y-intercept is 0, -3. So that's somewhere around here. So I'm going to extend the line, and the slope is going to probably look something like this. The steepness of the line is going to be something like this, or close to. And I would know that as performing the rise over run method. Here you have the y-intercept. Here in the other equation is 1. This one here is going to be 0, 0, 1. So this is 0, -3. And then this is going to be 0, +1. So the slopes are the same. So the steepness are the same. And this is what we have right here. So solving this problem or determining whether this is a inconsistent or consistent, or the equations being dependent or independent, can be determined by this method that I've used right here to find out this answer. However, so according to your notes from the last couple of videos, we see that this here, this system has no solutions, no solution. And since there's no solution, the since there's no solution, the equations are in fact independent. They are independent. So this is a great example for that. Remember, I said also too now, showing you another way to this problem, showing you another way how to look at this problem numerically. You can use the addition method, or the addition method slash the elimination method to determine it. Remember, I said if one side of the equation is different from the other side of the equation, then it's no solution. No two numbers can equal one another unless they are the same. And that the numbers are the same, like for example, what I said before, -3 is equal to -3, or 2 is equal to 2, or 5 is equal to 5, or 1/2 is equal to 1/2. Then those solutions are, that equation is infinitely many solutions. But if you have a number that is different, like 0 is equal to 5, 3 is equal to 10, -2 is equal to 12, then that will imply or suggest that this system of equation is in fact it has no solution, no solutions. So this let me show you another way in doing this problem. So I will clear this board here. Another way in doing this problem is to use the substitution method. 2x minus 3 is equal to y. Here we go. And then y minus 2x is equal to 1. We can use the substitution method to verify that this system has no solution. So since the y is already eliminated, or should I say isolated here, then we want to substitute this equation or this expression into the other equation. So this will be 2x minus 3 minus 2x is equal to 1. So now we just do simple simplification here. So look at this. So this here, this has become 0. 2x minus 2x is 0. Minus 3 is equal to 1. So negative 3 is, in this case, is equal to negative 1. However, negative 3 cannot equal to 1. So therefore, this system has no solution, and it's independent. Everybody see that? So remember we said for systems that have no solution, you can't have a different number equal to different numbers equal to one another. Like for example, in this case, negative 3 cannot equal negative 1, or 2 being equal to 5. Well, 2 can't equal to 5. So if you come up with this type of situation, then you know that the system has no solution. And also another way to understand is if you have a slope or a system with the same slope, the system has the same slope, then you know automatically that the lines will be parallel. However, it may not necessarily mean that it's going to be no solution, because those intercepts or whatever, or whatever values that you get on one side of the equation as opposed to the other side of the equation, they may or may not equal to one another. So you have to work the whole problem out. You know that if the slopes are the same, you know that your lines are going to be parallel. And it's a possibility that it may become a system that has no solution, or, in this case, infinitely many solutions. But not in this case. This case right here, what we're watching here, is a system that has no solution. But when we're going to look at an example where we have the slopes that are the same, but you're going to end up with values at the end of working out the problems to be the same. That means that the graphs somehow are overlapping each other, with the graphs being the same exact graph or equation. The graphs are basically they are the same, but one graph might seem to be different. But in a case, the graphs might, one graph might be different, but if you simplify the graph, right, the one of the equations, or simplify one of the equations, it's going to look exactly like, or it's going to be exactly like the other equation, which means those two equations are going to be overlapping each other when you actually graph the system. So let's do an example. Let's do an example of that right now. So I'm going to find an example that has infinitely many solutions. Let's look at this. Let's clear our board here. And let's look at this one. Look at this type problem. This problem here is, say we have 2x plus 3y is equal to 1. Then we have 4x plus 6y is equal to 2. Now, in this case, here's what's happening. If you actually take this and solve it using the addition problem, or should I say the elimination technique, I'm going to multiply 2 to the top equation, again, so that the numbers, or coefficient, or should I say term that I'm trying to eliminate, the coefficients to whatever variable you're trying to eliminate must be the same, but what did I say? Opposite of one another. So we use the distributive property, negative 4x minus 6y is equal to negative 2. And here we have, this is equation 2, this is plus 6y is equal to 2. So look at this. As we actually take this, look what happens. 0 plus 0 is equal to 0. So look at this. 0 is equal to 0. Those two values are the same. That's legal. You can have a number, you can have a system that has, once you solve or simplify, the both numbers on one side of the equation is equivalent to the other side of the equation, will give you an understanding that, in fact, that this suggests that this system has infinitely many solutions. And with this having infinitely many solutions, this system is consistent but dependent. The equations are dependent, and they're dependent on each other. So you remember, consistent uh, systems have at least one solution. In this case, is infinitely many solutions, but the equations are dependent. Remember, in the first video, we showed an example of that. Now let me show you why that is. Because if you actually simplify this equation, meaning if I take these two equations and put them into slope-intercept form, that is. So I'm going to take 2x plus 3y is equal to 1. And here I'm going to subtract here, take negative 2x to both sides, and then solve for y. So 3y is going to equal to negative 2x plus 1. So when we divide this to both sides, this is what this equation will simplify to. So this will be negative 2/3 x plus 1/3. You see this? So if we do the same thing to the other equation, right? 4x plus 6y is equal to 2, and we take negative 4x to both sides, then 6y is equal to negative 4x plus 2, and we divide 6 to both sides. If we simplify this here, 4 over 6, that's actually going to end up being negative 2/3. And then 2 over 6, right, is going to be 1/3. So you're going to wind up with the same exact equation. So when you graph both of these systems, they're going to overlap one another. Remember from the first video, we had an example like that, right? So this equation is good. And so this equation and that equation are the same. The slopes are the same, so it's going to have, they're going to be parallel, but parallel lapping over top of each other at one time. So that's going to give you significantly numbers that are just infinitely many, right? So the graph will look something like this. So let's change boards here. And we said that this was y is equal to negative 2/3 x plus 1 over 3. So basically, this is just a sketch. Nothing exact in a sense. This is your x, your y-axis. So basically, you have a negative slope, right? 1/3 if you have, say, 1, you have, let's just say 1/3 or 1/3 is somewhere here. Okay. So the graph itself is going to look something like this because it has a negative slope. If you actually take uh, and graph it again from the other equation, from the first equation and the other equation, just rewriting this down again. Let me tell you what. Let me use this and let me use different colors here. So actually, what were we doing? This. Well, I'll just keep it as I say. Y'all have an understanding that this. You had 2x plus 3y is equal to 1 and 4x plus 6y is equal to 2. The second equation, if you was to actually graph this, let me just use another. And if you was to actually, it'll go over top, it'll overlap this. See, it'll overlap this. So basically what I'm saying is if you actually take this together like this and set both of these equations equal to each other. You remember this from the other video. If you set this equal to both each other and we got variables on both sides, so when you got variables to both sides, you want to what? You want to get all the variables to one side. Get all the variables to one side. When we get all the variables to one side, I'm going to add 2/3 to both sides here. I don't like that dot being there, so I'm going to try to attempt to erase it without the software being difficult to me. So I have to, okay, so hopefully it'll take me back to my mode again. Sorry for the sloppiness, folks. But down here, this is what we'll get. We'll get, let me erase that. That's just, I don't like that. Everybody, if you know me, if you had me as a professor, you know I'm a stickler for neatness. Can't stand sloppy work. Okay, this is 1/3. I forgot to put 1/3 here. This is 1/3. There we go. So 1/3 in this case, if we go 1/3 to this side is equal to same to this side as what? 1/3. Because 2/3 x minus negative 2/3 x plus 2/3 x is 0. And negative 2/3 x plus 2/3 x again is 0 on this side. So we got 1/3 is equal to 1/3. So here in this case, again, proves and suggests that this system is consistent because it has infinitely many solutions. And it's what? Equations are what? Dependent on each other. Dependent. So that concludes this video.